Myself Shweta and I am from BSc Chemistry Honors 3rd year and my roll number is 34. Electronic spectra. Introduction. It has been discussed in the last chapter that when molecules absorb energy in the microwave region, transitions between the rotational level takes place, giving rotational spectra. Similarly, if the energy is absorbed in the near infrared region, transitions takes place between the vibrational levels accompanied by those in the region rotational levels, giving vibrational rotational spectrum. However, if the light is absorbed in the visible region or ultraviolet region, electronic transitions takes place, giving electronic spectra. A number of other processes also take place on absorption of light called photoprocesses. These may be photophysical processes such as fluorescence and phosphorescence or photochemical reactions. The branch of science dealing with such processes is known as photochemistry. In the present chapter, we shall take up a brief study of electronic spectra, whereas photochemistry will be discussed in the next chapter. Electronic transitions and band spectra. 3.52.1 Theory of electronic band spectra. Just as there are electronic energy levels in an atom, there are electronic energy levels in a molecule. However, there are no simple formula available for the energies of these electronic levels. Electronic spectra are obtained when the electrons in a molecule are excited from a lower electronic energy level to a higher level. However, as the electronic transition is accompanied by vibrational and rotational transitions, the total energy of the molecule in any state is the sum of electronic energy, vibrational energy, and rotational energy. ER represent the electronic energy, vibrational energy, and rotational energy of the molecule in the initial state before transition, and EV- and ER- are the corresponding values in the final state after transition. Then we have energy of the molecule in the initial state. E is equal to EE plus EV plus ER. Energy of the molecule in final state. E is equal to EE dash plus EV dash plus ER dash. Energy change involved in the electronic transition will be given by del E is equal to E dash minus E. सो यहाँ पर ई डैश की वैल्यू हो गई सारी डैश की वैल्यूज़ माइनस में सिंपल ई की जो इनिशियल स्टेट के एनर्जी मॉलिक्यूल्स की एक इक्वेशन थी वो डाल दी. तो ई डैश माइनस ई वी डैश माइनस ई वी प्लस ई आर डैश माइनस ई आर. तो यहाँ पर चेंज ऑफ ई मतलब एनर्जी किसकी इलेक्ट्रॉनिक एनर्जी की. ठीक है. फिर ई वी डेल ई वी वो वाइब्रेशनल एनर्जी प्लस डेल ई आर रोटेशनल एनर्जी. बट अकॉर्डिंग टू प्लैंक्स क्वांटम थ्योरी डेल ई इज इक्वल टू एच म्यू इज इक्वल टू एच सी म्यू बार. एच सी म्यू बार इज इक्वल टू डेल ई प्लस डेल ई वी प्लस डेल ई आर. एंड जो म्यू बार है इज इक्वल टू डेल ई प्लस डेल ई वी प्लस डेल ई आर बाय एच सी. एज फॉर अ पर्टिकुलर इलेक्ट्रॉनिक ट्रांजिशन so that del E remains constant, and for a particular vibrational transition so that del EV remains constant. Del ER can have different values due to different rotational transitions within the same vibrational energy change of the same electronic energy level. A number of closely spaced lines are obtained. This constitutes a band. For each vibrational transition, separate band will be obtained. Thus, due to different vibrational transitions for a particular electronic transition, a set of bands is obtained called band group or band system. Each electronic transition will give a band system, and hence the complete electronic spectra involving different electronic transitions gives rise to a series of band groups. Thus, the electronic band spectrum obtained for a gas molecule is quite complex. In spite of the complex nature of the electronic band spectra, these are preferred over the other types because these are obtained in the visible and ultraviolet regions so that these can be easily photographed and studied. So 3.52.2 Calculation of dissociation energy of molecules. A study of the electronic band spectrum reveals that at one end of the spectrum, the distance of separation between lines becomes smaller and smaller till ultimately the line spectrum vanishes and space of continuous emission starts. The frequency corresponding to the point where the line spectrum vanishes is the frequency necessary for dissociation of the molecule into atoms. Thus, electronic band spectrum can be used not only for getting the information as given by the vibrational rotational spectra, but it can also be used in evaluating the dissociation energies of the molecule. 3.53 Potential energy curves and Frank Condon principle. The explanation of electronic band spectra and dissociation energy can be early understood in terms of potential energy curves and Frank Condon principle. The potential energy curve of a diatomic molecule is obtained by plotting the potential energy of the system versus internuclear distance between the two approaching atoms. The curve obtained is of the shape. However, even at the minimum energy position, equilibrium position represented by point X, the atoms are vibrating so that the internuclear distances keeps on changing. Therefore, the potential energy keeps on oscillating about the minimum position. The vibrational levels thus occupied by the system may be represented by horizontal lines and indicated by appropriate vibrational quantum numbers. If sufficient energy is supplied so that the system occupies the vibrational level represented by Vd, the corresponding internuclear distance should become infinity, that is, the molecule should dissociate into atoms. However, this usually does not happen because before this stage is reached, the electron jumps to the higher energy level. That is, electronic transition takes place and the dissociation will take place only of the molecule in the higher energy level. Now, every electronic state has its own potential energy curve. Two such curves for the lower electronic states by 1 and second respectively. They differ in the fact that the minimum of the potential curve for the excited state second is at large internuclear distance than the ground electronic state 1. The dissociation energies for the two states are different as shown in figure. D2 is less than D1. This is evidently due to the fact that the bonding in the excited state is weaker than in the ground state. The vertical distance between the minima of the two curves gives the difference between the electronic energy of the two states. The transition between the two electronic states takes place according to the Frank Condon principle. According to this principle, nuclei being much more massive than electrons, and electronic transition takes place much more faster than the nuclei can oscillate to change their electronic internuclear distance. An electronic transition takes place from an extreme end of a vibrational level, example from A or D, because the velocity or vibrational energy of the atoms is zero at these positions and they spend maximum time at these points. As internuclear separation remains the same, the transition can be represented by a vertical line from point A dash to point C of the upper curve, and not from potential energy minimum of a lower curve to that of upper curve, the new vibrational level must be one which is nearest to point C. Counting levels, it appears that the excited molecule will be in the third or fourth vibrational level of the state second. This explains why in the electronics transitions there is no simple selection rule for the transition among the vibrational levels. All types of transitions from lowest vibrational level to any of the vibrational levels of higher electronic states are possible. It may be mentioned here that according to quantum mechanics, the transition from the lowest level V is equal to 0 takes place from the midpoint of the vibrational level, is the equilibrium or the most probable position, and not from the extreme positions. Each vibrational level has a large number of closely spaced rotational levels which have not been shown in the diagram. Now, when the transition takes place from vibrational level of the lower electronic state to some vibrational level of the upper electronic state, it is accompanied by a number of transitions between the rotational levels. The result is a group of closely spaced lines called a band. Since a number of vibrational transitions takes place, a group of bands called the band system is obtained. As the transitions takes place between many different electronic states, the result is electronic band spectrum consisting of several band systems. If electronic transition similar to A dash C takes place, the result is an absorption spectrum consisting of a number of vibrational bands. If, however, a transition similar to BD takes place where point D represents the vibrational electronic spectrum of diatomic molecule, as shown in figure 3.39, in case of diatomic molecule, when a photon is absorbed by the molecule, the most probable electronic transition that takes place is from V is equal to 0 of the lower electronic state to V is equal to 2 of the higher electronic state. This is called a 0 to 2 transition. Other transitions from V is equal to 0 level of the ground electronic state to different vibrational levels of the excited electronic state also takes place, but with much lower probabilities. Thus, the transition 0 to 2 has the maximum intensity, whereas other transitions have smaller intensities. Selection rules for electronic transitions in molecules. In order to understand selection rules for electronic transition in molecules, we should first understand a few minutes and symbols to be used. Parity. Parity represents the behavior of an orbital with respect to inversion. It is used for molecular orbitals of homonuclear diatomic molecules. We consider a point in the molecular orbital and not the sign of the orbital. Then we travel equal distance through the center of the molecule to a point on the other side. If at this point the orbital has the same sign, it is said to have even parity and is denoted by G. If the orbital has opposite sign, then it is said to have odd parity and is denoted by U. The parity designations apply only to homonuclear diatomic molecules because heteronuclear diatomic molecules do not have center of inversion. and there is a diagram of parity of an orbital. Second is multiplicity of state. The ground or excited electronic state of any species may have one or more unpaired electrons with spin in the same direction or opposite direction. If S represents total spin quantum number, then 2s plus 1 gives the spin multiplicity of the state. If S is equal to 0, multiplicity of a state is equal to 1. Similarly, O2 in the ground state has two unpaired electrons with parallel spins. Its multiplicity is equal to 3. Term symbols of molecules. These symbols give complete information about the state of the molecule, that is orbital angular quantum number, depending upon the component of the total angular momentum about internuclear axis. First one is the single electron in H2 positive in sigma molecular orbital has zero orbital angular momentum, hence the term symbol is summation. Further, it has multiplicity is equal to 2. The term symbol for any closed shell homonuclear diatomic molecule is 1 summation g because the spin is 0. As all the electrons are paired, there is no orbital angular momentum from a closed shell and the overall parity is g. If there is only one pi electron outside of a closed shell, its orbital angular momentum about the internuclear axis is equal to 1 unit. Hence, the term symbol is pi. If there are two pi electrons as in O2, the term symbol may be summation or pi. The term symbol summation will be used if the electrons are orbiting in opposite directions, which can be so if they occupy different orbitals. The term symbol pi will be used if the two pi electrons are orbiting in the same direction, which can be so if they occupy the same pi orbital. In case of O2 in the ground state, the two pi electrons occupy different orbitals with parallel spin and the overall parity of the molecule. Hence, the term symbol is 3 summation g. First, only those transitions are allowed between the states for which the difference in the component of the orbital angular momentum along the z-axis is 0 or plus minus 1. The transitions are allowed only between the states having same multiplicity. The singlet and triplet transition may occur, but singlet triplet transitions are forbidden. Only those transitions are allowed which are accompanied by a change in parity. Those transitions are forbidden. This is known as Laporte selection rule. The most common molecular orbitals present in a molecule are the bonding molecular orbitals. Sigma and pi are the corresponding anti-bonding molecular orbitals. Sigma star and pi star. Besides these, there may be heteroatoms such as N or O present in the molecule which have orbitals containing lone pairs of electrons. As they are non-bonding orbitals, they are designated as N orbitals. They don't have any corresponding anti-bonding orbitals. In case of homonuclear diatomic molecules such as H2, N2, etc., the highest occupied molecular orbital HOMO in the ground state is a bonding molecular orbital BMO, whereas the lowest unoccupied molecular orbital LUMO is an anti-bonding molecular orbital ABMO. The electronic transition takes place from HOMO to LUMO and absorption of suitable energy. So there is a diagram. The transition may also take place from n orbital to the anti-bonding molecular orbital. In other words, the electrons may be excited from form sigma, pi and n orbital. Thus, transitions which are allowed are sigma to sigma star, pi to pi star, n to n star, n to pi star or n to sigma star. Further, it is interesting to point out that if a single electron excited from the lower orbital to the excited antibonding molecular orbital has a spin opposite to that of the electron left in the lower orbital, if the two electrons in the upper and lower orbitals have parallel spins so that 2s plus 1 is equal to 3, the excited state is triplet. Thus, the excited states are classified as singlets or triplets. The triplet state has lower energy than the singlet state in accordance with the Hund's rule. As already explained, Otto in the ground state is in the triplet state. It shows an exceptional behavior as the electronic transition takes place from triplet ground state to triplet excited state instead of singlet excited state. That is why the spectrum of O2 molecule is quite complex. The types of transitions which certain categories of compounds undergo and the reason or the wavelengths absorbed before these transitions are given below. First, saturated hydrocarbons or compounds containing CC and CH single covalent bonds require very large energies to produce electronic excitations, usually beyond 160 nanometer. In such molecules, sigma to sigma star transitions takes place. A simple olefin has an absorption band at about 170 nanometer. In such molecules, pi to pi star transition takes place. Molecules like methylamine and methyl iodide, which do not contain pi orbital, undergo N to sigma star transitions. All electronic transitions in organic compounds do not occur in the ultraviolet region. The occurrence of colored compounds indicates absorption of radiation in the visible region. Compound containing N double bond N group or long conjugated system including aromatic rings absorb at a wavelengths greater than 180 nanometer. That is why they look colored. Such groups are chromophores. In such cases, the energies of the molecular orbitals lie close together and pi to pi star transition takes place. Example, the protein beta carotene has a fairly long conjugated system and shows absorption at about 240 to 280 nanometer. Intensity of electronic bands. The intensity of any electronic bands depend upon the extent of overlap between the wave functions of the ground state and the excited state. Greater the overlap, greater is the intensity. As there is very poor overlap of the wave functions in the n to pi star transition and there is excellent overlap in the pi to pi star transition. The intensity of the band produced by N to pi star transition is very low as compared to that produced by pi to pi star transition. Further, in the presence of any acid, the electrons of the n orbital undergo protonation and thus N to pi star band disappears. Thank you, and this is the chapter of electronic spectra.